In this question, we were told that the acceleration of a particle with respect to time was given by this equation, p times t squared minus q times t cubed. We're first asked to find the velocity. Now, notice here that the acceleration is not constant. P and Q are constants, but the acceleration itself is dependent on time. So that means that we cannot use the toolbox equations to solve this. Instead, we have to use calculus. And the way that we would do that is we would solve for the velocity. I suppose if we really wanted to be anal about it, we would write A and V like that. We would solve this by taking the integral of pt squared minus qt cubed dt. Now, the integral of pt squared, this term over here, will be, we raise the exponent by 1, that's t cubed, and we divide the coefficient by the new exponent. Minus, we would do the same thing over here. T cubed becomes t to the 4th, and this now becomes q over 4. And finally, we add the plus c. Now, we were told that the velocity at a time of 0 was equal to 0. So that means that if I plugged in 0 for t, like this, I would get 0. So 0 cubed is 0, so this first term cancels out. 0 to the 4th power is also 0, so this term cancels out. So I just end up with 0 is equal to c. So the overall expression for the velocity is, the velocity as a function of time is equal to p over 3 t cubed minus q over 4 t to the 4th. Now that we have the velocity over here, the full velocity function, let's figure out what the position function must be. The position function is found by taking the integral of the velocity. So, position with respect to time is equal to the integral of p over 3 t cubed minus q over 4 t to the 4th dt. Now, the antiderivative of t cubed is going to give us t to the 4th, and since we have to divide this coefficient by 4, this now becomes p over 12, minus the antiderivative of t to the 4th is t to the 5th, and if we have to divide this coefficient by 5, that's going to give us q over 20. And then we have the eternal plus c. Now, we were also told that the position at a time of 0 is equal to 0. So we plug 0 in for all of the times over here, and we get that 0 is equal to p over 12, 0 to the 4th power, minus q over 20, 0 to the 5th power, plus c. Again, this entire term will cancel, this entire term will cancel, and we again end up with c is equal to 0. So, the position as a function of time is equal to p over 12 t to the 4th minus q over 20 t to the 5th. And since I have talked about these as vectors, well, we really should put an I hat after them. The thing is that you get to set your axes whichever way you want, and since this is a one-dimensional equation, we might as well just set our axes so that everything is taking place along the x-axis. So I could put an I hat here, and an I hat here, and an I hat here. And this then would be the solution. This would be the position with respect to time. This would be the velocity with respect to time. In this question, we were told the velocity. The velocity is equal to 2 plus 0.25 times t to the negative 1 power. Now, I think we were given A and B, and then we were just told what these coefficients are. No matter. The point is that obviously the coefficients are not changing, so I will just use these numbers for those coefficients. The first thing we were being asked for was the acceleration. So this is v of t. So now let's solve for acceleration with respect to time. The acceleration is the derivative of the velocity. So derivative of 2, that's 0, plus derivative of 0.25 t to the negative 1. So the negative 1 is going to get multiplied by the 0.25. That gives us negative 0.25. And then we drop this exponent by 1, t to the negative 2. So that works out to negative 0.25 t to the negative 2. We were also asked to find what the value of acceleration is at the time of 2 seconds and at the time of 5 seconds. So the acceleration at 2 seconds, first of all, let me put this as the solution here. The acceleration at 2 seconds would be negative 0.25 times 2 to the negative 2 power. So 2 to the negative 2 power would be 1/4, and negative 0.25 multiplied by 1/4 is going to give us, oh, I can't do that in my head. I think it's going to be negative 0.0625. So that would be the value of the acceleration at time equals 2. What about at a time of 5? Then we would have negative 0.25 times 5 to the negative 2 power. So 5 to the negative 2 power is 1/25. When you solve that out using your calculator, you're going to get negative 0.01. Now, the other part of the question was asking us to find an expression or an equation for the position, that is x of t. And the way that we do that is by taking the integral of 2 plus 0.25 t to the negative 1 power, dt. So the antiderivative of 2 is 2t, and the antiderivative of 0.25 t to the negative 1 power is 0.25 ln of t. Remember, the antiderivative of t to the negative 1 is ln of t. And then I add the c to it. Now, we were told that the x of 1 is equal to 0. So if I were to plug in 1 for t over here, I would get that 0 is equal to 2 times 1 plus 0.25 times the ln of 1 plus c. Now, 2 times 1 is 2. The ln of 1 is 0, so this entire term cancels out. So I'd be left with a c over here. So that's going to give me that c is equal to negative 2. So our entire expression for the position is going to become 2t plus 0.25 ln of t minus 2. Now, let's solve this out at 2 different times. At a time of 2, I would need to use my calculator for this because I can't calculate ln's in my head. But let's see. At a time of 2, 2 times 2 plus 0.25 ln of 2 minus 2 gives us 2.17. So the position here would be 2.17. And that would be in meters, and we could consider that to be an I hat as well. What about at a time of 5 seconds? Again, we would put this into our calculators. So 2 times 5 plus 0.25 times the ln of 5 minus 2 gives us 8.40. So the position at 5 seconds is 8.40. And this now would be the position and the acceleration at the times of 2 seconds and 5 seconds for a particle which has this velocity. In this case, we were given our first acceleration, which was in 2 dimensions for the first time. Now, given this acceleration, we needed to find the velocity. No problem. Velocity is just the antiderivative of the acceleration. So all we have to do is take the antiderivative of this. Now you might be wondering how we would do that. What we have to do is we have to treat the i's and the j's separately, just like we do for any other operation. So another way to write this would be the integral of 4 dt times I plus the integral of 3 dt times j. So now this becomes easy. The integral of 4 is 4t plus c, and the integral of 3 is 3t plus c. Now, we need to figure out what c is. We were told that at time equals 0, that the velocity is equal to 0. So, if we plug in 0 for t over here, we can solve for what c must be. We are told 0 is equal to 4 times 0 plus c. Let's call this c1 and let's call this c2. I hat plus 3 times 0 plus c2. As you probably guessed, 4 times 0, that becomes 0, so that means that c1 must also be 0. 3 times 0 is 0, so that means that c2 must also be 0. So we end up with the velocity as a function of time is equal to 4 times t I hat plus 3 times t j hat. Now, let's solve for the position. We are told the velocity, or we found the velocity just a moment ago, so the position is just going to be the integral of that velocity. So the integral of 4t I hat plus 3t j hat dt. Again, we would break this into 2 separate integrals, like this. Integral of 4t dt I hat plus integral of 3t dt j hat. So, this is now going to become integral of 4t, that's 2t squared, plus c. And integral of 3t is going to be 1.5 or 3 over 2 t squared plus c. Let's call this c1 and let's call this c2. Now we need to figure out what c1 and c2 are. Again, we were told that at time equals 0, that x equals 0. So that means that 0 is equal to 2 times 0 squared plus c1 I hat plus 3 over 2 0 squared plus c2 j hat. Again, this cancels, c1 must be equal to 0, and this cancels, so c2 must be equal to 0. So we end up with x of t is equal to 2t squared times I hat plus 3 over 2 t squared times j hat. And this would be the position with respect to time. The next part of this question asked to graph out what the position would look like over time. Now, this should be pretty straightforward to do. So let's go ahead and let's figure that out. At x equals 0, you could make a table over here. Like, let's say this is the time, this is the I hat position, this is the j hat position. So at a time of 0, I hat, you would plug in 0 over here, 0 over here. You would end up with 0 for I hat, 0 for j hat. Now, when you start plugging in for other values, you would get more information about where this position is, where this object is over time. So what about for 1? Well, put in a 1 over here, you get 2, and put in a 1 over here, you get 3 over 2. What about 2? 2 squared is 4, times 2 is 8. 2 squared is 4, times this over here would be 6. What about 3? 3 squared is 9, times 2 is 18. 3 squared is 9, times 3 over 2 would give us 27 over 2. And I think that ought to be enough to get started with. So we could draw a graph over here. And we could set this as being the I hat direction, this as being the j hat direction. And let's say it stretches out something like this. So 0, 0. 2 and 1.5 would be right about here. That's its position after 1 second. 8, 6 would be about here. That's its position after 2 seconds. And 18, 27 over 2 would be its position after 3 seconds. So what we see is that it's moving in a path like that. I can draw this in another color. You don't need to be hugely exact about it. But what we do see is that it is accelerating in both the x and the y directions, and this is producing a path that looks like that. For this question, we were told that the position is given by 3t I hat, or sorry, 3t squared I hat minus 7t cubed j hat minus 5t to the negative 2 k hat. So this is a three-dimensional vector. That's all right. Three-dimensional vectors work in virtually the same way as two-dimensional vectors. So first we're being asked to find the velocity. No problem. Velocity is the derivative. So we have to take the term-wise derivative of each one of these directions. So I hat is going to become 2 multiplied by 3 is 6 times t minus j hat 3 times 7 gives us 21, and the 3 drops down to a 2. And in the k hat direction, negative 2 times negative 5 gives us plus 10, and this exponent now drops to a negative 3. Now the first thing we were being asked for is what is the position of, or sorry, what is the velocity of this particle at a time of 2 seconds? So we need to substitute t equals 2. Let me first write a box around here. That way we know that this is the equation we're going to consistently refer to. The velocity at 2 is equal to 6 times t would be 12, minus t squared is 4 times 21, that would be negative 84, plus t to the negative 3, that would be 1/8. So 10 over 8, which would be the same thing as 5 over 4. That would be the velocity of this object at a time of 2 seconds. We were also being asked to find the speed of this object. So to find the speed, what we would do is we would basically take Pythagorean theorem across all 3 of these terms. So there's 2 ways of doing this. Either we could substitute everything in and then solve for the speed by taking Pythagorean theorem, or we could do Pythagorean theorem first, come up with an expression, and then solve for the speed. Personally, I like doing it the second way, so let's try it out and see what happens. The speed is going to be equal to square root of the first term squared plus negative 21 t squared, also squared, plus 10 times t to the negative 3, also squared, which works out to square root of 6 times t whole squared would give us 36 t squared, plus negative 21 squared is going to be 441. T squared squared is going to be t to the 4th. Plus 10 squared is going to be 100. T to the negative 3 to the squared is going to be t to the negative 6. Okay. Now, offhand, I don't see a way of simplifying this, so I'm just going to leave it like this, in this expression over here. Now, we were being asked to find the speed at a time of 1, so that would be v at a time of 1, which is going to be square root of 36 times 1 squared, plus 441 times 1 to the 4th power, plus 100 times 1 to the negative 6th power. So 1 squared, obviously, that's going to be 1 in every one of these cases. So we end up with 36 plus 441 plus 100. So 36 plus 441, that would be 477. Plus 100 is going to give us 577. And the square root of 577, well, I can't do that in my head, so whip out our calculators to do that. That would be 24.02 meters per second. So that is the speed of our particle when it is at t equals 1 second. Now, the next question was, what about at t is equal to 3 seconds? Here, we're going to have to use our calculators. So we would do the square root of 36 times 3 squared plus 441 times t to the power of 4 plus 100 times 3 to the power of negative 6 gives us 189. So that would be the speed at a time of 3 seconds. The next part of this question was finding the average velocity. between the times of 1 and 2 seconds. So the way that we do this is we find the position at a time of 2 seconds minus the position at a time of 1 second, and then divide the whole thing by 2 minus 1 is 1 second. That would be our t. So let's find everything that we know. If I plug in 2 into this position over here, 2 squared is 4 times 3 is 12. So 12 I hat minus 2 cubed is 8 minus times negative 7, that would give us negative 56 j hat. 2 to the negative 2 power is 1/4. So this would be minus 5 over 4 k hat. Minus, what would happen if I put in 1 over here? Easy enough. This would become 3 I hat minus 7 j hat minus 5 k hat. And the whole thing would get divided by 1 second. So what does all of that work out to? 12 minus 3 divided by 1 is going to give us 9 I hat. Minus 56 j hat minus negative 7 is going to give us negative 49 j hat. And minus 5 over 4 k hat plus, because it's a negative negative, plus 5 k hat is going to give us plus 3.75 k hat. So that would be the average velocity of the particle between the times of 1 second and 2 seconds. Now, the last thing we were being asked to do was to find the acceleration with respect to time. And that's easy to do. For the acceleration, all we have to do is start with the velocity and then take the first derivative of that. So, derivative of 6t would be 6. Derivative of negative 21t squared would be negative 42t. Plus, or 10 times negative 3 would give us negative 30. And this would get dropped from t to the negative 3 to t to the negative 4. So this would be our acceleration in terms of time. In this question, we were told that the acceleration is constant. And if the acceleration is constant, then that means that this question basically reduces down to a standard kinematics case that can be solved using the toolbox equations. So we were told the initial velocity at the time of 0 was 10 in the I hat direction and 20 in the j hat direction. The final velocity after a time of 4 seconds was, let me draw this line here so that it becomes a little bit easier to read. The final velocity was 0, and the final velocity in y was 10 j hat meters per second. So the first thing that we're looking for is the acceleration in each direction. No problem, we can use toolbox equation number 1 to do that. In the x direction, acceleration times time is equal to v final minus v initial. So acceleration, unknown, time, 4, is equal to v final, 0, minus v initial, 10. So the acceleration is equal to negative 10 divided by 4, which is negative 2.5. What about in the y direction? In the y direction, you use the same equation, at is equal to v final minus v initial. So again, acceleration, unknown, time, 4, v final is 10, minus v initial is 20. So 10 minus 20 is going to give us negative 10. Negative 10 divided by 4 is again going to give us negative 2.5. So now we know that the acceleration of this object is negative 2.5 I hat minus 2.5 j hat. Now, we next need to find the velocity. The velocity is found by taking the antiderivative of each one of these terms. So that would be integral of negative 2.5 dt I hat plus integral of negative 2.5 dt j hat, which works out to negative 2.5 times t in the I hat direction. Oh, almost forgot the plus c. Let's call this plus c1 plus negative 2.5 t plus c2 in the j hat direction. So we need to find out what c1 and c2 are. We know that at a time of 0 seconds, the velocity was 10 I hat plus 20 j hat. So because that was our initial velocity, that will actually also be the values for c. So that means that the overall velocity is going to be negative 2.5 plus 10 in the I hat direction, 2.5 t times 10 in the I hat direction, plus negative 2.5 t plus 20 in the j hat direction. Whenever you're given a value of 0 and the only thing you have here is a bunch of t's, then that means that these initial values will be your values of c. So this then would be the velocity of this object with respect to time. Now the next thing is to find the position of this object with respect to time. Once again, we take the integrals. First I'll put a box around this. So the integrals would be over here for position, integral of negative 2.5 t plus 10 dt I hat plus integral negative 2.5 t plus 20 dt j hat. So when you solve this out, this works out to this t squared, this becomes negative 1.25 plus 10t plus c1 I hat plus negative 1.25 t squared plus 20t plus c2 j hat. I think we were told that it was starting from the origin, and if that's the case, then at time equals 0, these t terms will cancel out, and you'll be left with c1, which is equal to 0, that's the x-coordinate of the origin, and something similar will happen in the y direction. So since we're starting at the origin at t equals 0, that means that c1 and c2 will cancel out, and this then will be your expression for the position of the object with respect to time. In this question, we have a golfer who is standing on an elevation in the on the green, or on the course rather, and she puts the golf ball such that it will land something like this. Now, in this case, photo 1 will correspond to a nanosecond after she has struck the golf ball, and photo 2 to a nanosecond before it lands. I'm going to set my origin as being the initial location of the golf ball, and I will set rightwards as positive and upwards as positive. Let's write down all of the things that we know and all of the things that we have to find out. So the displacement in x is the thing that we are looking for. We want to find out how close the golf ball lands to a certain region of the golf course. We do know that the golf ball is overall going to descend by 20 meters. Because this is a projectile, acceleration is going to be 0 in x, negative 9.81 in y. So we're looking for the displacement in x. We are given one other piece of information. The golf ball was launched at an angle of 40 degrees and with a velocity of 20 meters per second. So, this is a vector in polar. We need to convert this into Cartesian or rectangular. Let's start. In the x direction, the velocity would be given by r cos theta, which is equal to 20 cos of 40 degrees which is 15.32 meters per second. What about in the y direction? That would be r sine theta, which is 20 sine of 40 degrees which is 12.86. So now we have three pieces of information in the y direction. We can use that to solve for the time, and then we use the time in the x direction to solve for the displacement. The three pieces of information are the displacement in y, the initial velocity in y, and the acceleration in y, and we're looking for the time. There's only one equation which weaves together all four of these quantities, and that is toolbox equation 2. So, delta y is negative 20 is equal to v initial was 12.86 times an unknown time plus 1/2 times acceleration, negative 9.81, times t squared. So this is a quadratic equation. I'm going to rearrange this somewhat. Negative 4.905 times t squared plus 12.86 times t plus 20 is equal to 0. So here is our quadratic equation. We can solve this using the quadratic formula. T is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's plug everything in. Negative 12.86 plus or minus square root of b squared, that's 12.86 squared, minus 4 times 4.905 times 20, all divided by 2 times negative 4.905, which equals negative 12.86 plus or minus, let's work this out, 12.86 squared minus 4 times negative 4.905 times 20. 557.78. And the square root of that is 23.62. All divided by negative 9.81. Now, if I were to add these together, that would give me a positive, but a positive divided by a negative would give me a negative. We're not dealing with negative times anytime in this course. So I have to take the negative side of it. Negative 12.86 minus 23.62. So negative 12.86 minus 23.62, all divided by negative 9.81, gives us 3.72 seconds. So that is the time that it takes for the golf ball to land. Now, suppose we were to find out what the range of the golf ball is going to be. That is looking for its displacement in x. So the way that we would solve that is again using the same equation. That is delta x is equal to v initial times t plus 1/2 a t squared. That's the only one of the toolbox equations that weaves together displacement, initial velocity, acceleration, and time. So let's plug in what we know. 15.32 times a time of 3.72 seconds plus half times an acceleration of 0 times time squared. This entire term is going to go away. So 15.32 times this time is 56.97. So the displacement of the golf ball is 56.97 I hat meters. Now, the question said that the golf ball, we wanted it to land 70 meters away. So this is a little bit short of that. This is how far the golf ball lands away from where it started, which is about 13 meters short of the 70 meters that we wanted it to travel. In this next question, we have an astronaut who kicks a soccer ball on Mars. The kick occurs on level ground. We will treat photo 1 as being an instant after it was kicked, and photo 2 as being an instant before it lands. Now let's think about what information we were told and what information we need to find out. This is Mars that we're talking about. And so this projectile motion problem that we have over here has to account for the fact that we are now in Martian gravity. Unlike Earth, where the acceleration due to gravity is negative 9.81, on Mars it's only negative 3.71. The acceleration in x, of course, is 0. By the way, I forgot to draw my origin and axes, so let's do that in our usual way. I'll set the origin at the location of the ball just before it starts. I'll call that the x direction, I'll call that the y direction. In the y direction, the ball lands at the same height that it started from. That's 0. And the other thing that we were told was, we were told that it was launched at a speed of 15 meters per second at an angle of 45 degrees. So, let's work this out. We need to break this vector, which is in polar, into its rectangular form. This would be v initial in y, and this would be v initial in x. So, in the x direction, v initial in x is equal to r cos theta, which is equal to 15 cos 45 degrees, which is equal to 10.6. Let's call it 10.61. So our initial velocity in x direction is 10.61 I hat meters per second. In the y direction, v initial in y would be our sine theta, which would be 15 times the sine of 45 degrees. But it just so happens that the sine of 45 and the cos of 45 are the same thing. So 15 sine 45 is also going to work out to 10.61 I hat meters per second. Now, we're looking for the range on the moon. So, we're looking for the range on Mars, so that would be the displacement in x. So what we're going to do is, we're first going to solve for the time using the information in y, and then we're going to solve for the displacement in x. So, to solve for the time, we have displacement, we have initial velocity, we have acceleration, we're looking for time. There's only one equation that weaves all four of those together, and that is toolbox equation number 2. Delta y is equal to v initial y times t plus 1/2 acceleration times t squared. So delta y 0 is equal to v initial, which is 10.61, times time, which is unknown, plus 1/2 times negative 3.71 times time squared. Now I can simplify this by dividing everything by time. I can also take 1/2 of 3.71, that would be 1.805, I think? No, 1.855. Let me just check that. 1.855. Okay. So, dividing everything by time and moving this term to the other side, I would end up with 1.855 t is equal to 10.61. So now I just need to divide both sides by 1.855. So 10.61 divided by 1.855 gives me 5.72 seconds. Now we have 3 pieces of information in x, and we can easily solve for the displacement using the same equation. Delta x is equal to v initial times t plus 1/2 a t squared. So that's equal to v initial, 10.61, times t, 5.72, plus half acceleration, 0, times t squared. I'm not even going to bother with this because the acceleration is 0. The whole term will cancel out. So that will give us 10.61 multiplied by 5.72, which is 60.69 meters. So that would be the range on Mars. The second part of this question was asking what happens if exactly the same soccer ball is kicked in exactly the same way, but this time we're on the moon. On the moon, acceleration due to gravity is negative 1.63, much smaller than what it is on Earth or even on Mars. So let's first find out how long it takes for the soccer ball to land. The process will be exactly the same as before. Delta y is equal to v initial times t plus 1/2 a t squared. That's the toolbox equation that we need to use to solve for the time. So delta y is 0, v initial is 10.61 times t plus 1/2 times acceleration, 1.63 negative, times t squared. Now I can cancel out a time from both sides. Half of negative 1.63 would be negative 0.815, and if I were to move that to the other side, I would get 0.815 t is equal to 10.61. So now let's solve for t by dividing both sides by 0.815. 10.61 divided by 0.815 gives us 13.02. Okay, so that is the time that would be required for this soccer ball to land. Now, let's solve for the displacement, which is what we were actually looking for in this first place. The displacement can be solved using exactly the same equation. In this case, the acceleration is 0. V initial is 10.61 times the time of 13.02 plus half times acceleration, 0, times t squared. I won't even bother with that. This entire term is going to cancel out. So 10.61 times this answer of 13.02 gives us 138.13 meters. So that is the distance, that is the displacement, rather, of the soccer ball when it is kicked on the moon.